Hi lads, we'll have a look at a rates of reaction question in this video. So the first part of it there, what is meant by the rate of a chemical reaction, so that's relatively straightforward. It's a change in concentration per unit time of one of the reactants or products. And remember, you can whether it's the decrease in the amount of reactant, whether that's mass or volume, or number of molecules, or indeed the increase in the amount of products, again mass, volume, or whatever way you're measuring the production of the product. In an experiment then, 25 cm cubed of a 0.1 molar sulfuric acid solution was added to excess granular zinc. So this is an acid and a metal, which always gives rise to hydrogen gas and a salt. The hydrogen gas evolved in the reaction was collected in the volume at room temperature and pressure. So room temperature and pressure is normally assumed to be 25 degrees Celsius and 101 kilopascals, and measured regular time intervals. The results obtained were as following tables. So you have 0, so it's done every minute, and then that's the volume reduced every minute. And you see from in this first minute, from 0 to 1 minute, 30 cm was produced. Cm cubed was produced, whereas if we go from maybe minute 7 to minute 8, you only have the production of 0.5. So even from that, you can see the initial rate is very, very quick. I mean, that minute is the same length as that minute there. For in 7 and 8, that's 60 seconds, that's 60 seconds. In these 60 seconds, there's a difference of 30, and in these 60 seconds, there's a difference of 0.5. So you can think about things like that when you see the graph. Or see the table of results initially. The balanced equation, this is just a metal and sulfuric acid, or an acid, giving rise to a salt, zinc sulfate in this case. There's the zinc and there's the sulfate, SO4 2 minus and Zn2 plus in this case. And, zinc is a transition metal, obviously it doesn't have a constant or it has variable valency, but actually zinc is one of the interesting ones. That'll always form a Zn2 plus, but anyway, let's not get into that. And then H2 is hydrogen gas. I draw a piece of apparatus that you use to collect this. So the piece of apparatus we're talking about is just downward displacement of water. You draw something like this. You have the zinc, and then you have the 0.1 molar sulfuric acid added in there, and you so there's the zinc and there's the 0.1 molar sulfuric acid solution, and the two of those are mixed together, and then you have a stopper with some glass tubing in it. You could call this the delivery tube and mark that in the diagram really, and there's the bubbles of hydrogen gas, and the graduated cylinder allows you to measure the amounts, and always include a stop clock when you draw the diagram for this one. So that's that part. Using the balanced equation for the reaction, calculate the maximum amount of volume of hydrogen gas at STP which will be evolved. So essentially, guys, what you have here is we need to find out the maximum volume of hydrogen gas. There's the balanced equation, and we need to find out how much H2SO4. And when I say how much, I mean how much in terms of moles, number of molecules. And then it says excess zinc, so if you look up here, it says excess granular zinc. Therefore, we may assume that we won't run out of that. So what amount of this do we have? And we need to go up here and we look in the question, and we see we have 25 cm cubed of sulfuric acid, and that sulfuric acid has a concentration of 0.1 molarity, or 0.1 moles per litre. Remember that M right there stands for moles per litre. Now, if that means that, like, if you had a litre, if you had 1,000 cm cubed of it, then you could say that you have 0.1 moles. I mean, that's somewhat. Then you could write that down here and put it in there. But we don't know. Or what I should say is, we don't have 1,000 cm cubed. We don't have a litre. If we had a litre, it'd be 0.1 moles is what we had. But we only have 25 cm cubed of that. It's a bit like speed and time. I mean, if your speed is 25 kilometers an hour, does that guarantee that you have in fact travelled 25 kilometers? No, of course. You need to travel for a full hour to achieve that distance. To achieve this amount, 0.1 moles, we would need to have 1,000 cm cubed. So you need to think about that, because that's a litre. So therefore we want to find out not how much is in a litre, because we don't have a litre of it. We want to find out how much is in 25 cm cubed. The easiest way of doing that is if you know that you have 1,000 cm cubed, when you have 0.1, so I've done it out here in pen, so it's a 0.1 moles per litre solution. That would be 0.1 moles per litre. How much would there be in 1 cm cubed? That's normally the easiest way to do it. So, I mean, if you divide a litre, which is 1,000 cm cubed, if you divide that by 1,000 to get 1, you should do that to the number of moles as well, just to get it down in the same proportion, of course. That'll be 0.1 over 1,000. You could type in, you could write out all the zeros. I just left it as a fraction here. We have 25 cm cubes though. So what do you do to 1 cm cubed to get it up to 25? You multiply by 25. So if you like, we divided by 1,000 here, and then we're multiplying by 25 here to bring it up to how many moles there is in 25 cm cubed. So essentially that's the moles in a litre. That's the moles in 1 cm cubed, and that's the number of moles in 25 cm cubed. Simple as that. And then 0.0025 moles of H2SO4, that's what we have when you multiply 0.1 divided by 1,000 multiplied by 25. And that's 0.0025 moles of H2SO4. Then we go to the balanced equation, and that is essentially states that one of these reacts with one of these to give us one of these and one of these. Therefore, if I have that amount of H2SO4, well, one of those makes one of those, therefore 0.0025 moles of it, some amount of it, this amount of it will make this amount of it, or this amount of hydrogen. And that's assuming that we have excess of that, and by coincidence in this case they'll all be the same, because it's 1 is to 1 is to 1 is to 1. But really we only care about the relationship between the two of those to answer this question. And that's the amount of H2 produced. And then 1 mole, this is cut off on the page here, but 1 mole is 22.4 litres at STP. And then to get the number of moles that we don't have 1 mole. If we did, it would just be 22.4 litres, and we'd be finished at STP. Remember, that's standard temperature and pressure, which is 273 Kelvin, which is 0 degrees Celsius, and it is 100,000 pascals or 100 kilopascals. But in any case, that's just STP at this. We're not really concerned with that, perhaps, or at least we won't use those figures. We just know that 1 mole at STP occupies 22.4 litres. And what do you do to 1 to get 0.0025? Well, you multiply by 0.0025, of course, 1 times anything. And then just do the same to 22.4, and that'll give you the volume in litres, which is 0.056. That's that one. So we've those two done now. And then to plot the graph of the curve, and you do this on graph paper using the above table and comment on the shape of the curve. So there it is graphed on Excel. There's each time that was given to us. Make sure that these indentations are always equal, of course. The scale needs to be accurate, so go up in 5s and make sure every distance is exactly the same distance between each of those, and likewise along here. That might seem simple, but you'll be surprised. And that's effectively the graph of that. Then it does say to comment on the curve, so you could say that, like if I was to draw the slope of the curve here, that's quite steep. That means the rate is quick, if you like, at least quick in comparison to what, as you further on you go, you see that. Draw loads of tangents, you see it gets the rate of change, otherwise known as the rate of the reaction here, is becoming less and less until it's straight over and back, which gives rise to the rate going to 0, i.e. there's no product formed. The next part of the question then, it says plot your graph, that's that done. So I'd comment on the shape that say that the initial rate is very, very quick, and that is because, like any chemical reaction, when you have limited amounts of 1 or 2 of the chemicals, the initial rate will be fast because of an increase in collisions, or a maximum amount of collisions at least for that concentration. and temperature. And then as the reaction goes on, one or both of the reactants decreases in concentration. Well, both of them would decrease, but let's say you may start to run out of one of the reactants, giving rise to a slowing of the rate of the reaction. That's all that happens. The initial rate is high because of the high number of collisions, and then the reaction, as the reaction proceeds, the slope decreases because either one or both of the reactants is starting to reduce in number. Remember, amount is very important in chemistry, much better than mass. Then the amount of collisions, the amount of molecules present is decreasing, therefore the amount of collisions and the amount of collisions that are effective are decreased. And then if you look at the values, the reaction effectively stops at this point, at least from our graph. Now it could stop obviously anywhere between 8.5 and 9, but or 8 and 9, I think it's every minute is read in this on the table that we looked at. But essentially we know that it stopped there because there's no increase between here and here. So it's definitely stopped at 9 minutes. Now there's an argument, of course, it could stop anywhere between the two of those. It could have reached 9 back here at 8.25. Anyway, that's probably overcomplicating. Just remember that the reaction has come to a completion here at this point. This is just time. Time obviously goes on forever, so it's going to continue in that direction. That's that one. Find using the graph the rate of the reaction after 2 minutes, the instantaneous rate. Now guys, the way we did this, we looked at this before as well, but just to reiterate it again, draw your graph as you would normally, as we did earlier, and then take your ruler and draw. So go to 2 minutes, draw a straight line up and mark that point with a pencil, and then take your ruler and lower your ruler such that the ruler cuts or touches the curve, i.e. creates a tangent at one point only there. So don't twist the ruler that it cuts the curve twice. Make sure it touches it once and once only. And then pick any 2 points on that line. Forget about the curve then, just look at the tangent. So I picked this one because they're nice round numbers. If you go straight up, look at there, straight up from 1 and straight across 35, so that's the point. The x value, y value from maths, there's the x value and the y value, and there's the x value of another point on that, and there's the y value. There's the x value if you go straight down, and again you use graph paper so you get a nice accurate point, and 60. Again I'm drawing these lines on PowerPoint, so not very straight, but yeah, straight down you get 3.5, 60 is a point there. 3.5 on the x-axis, x value, 60 on the y value, and that's just simple coordinate geometry. Then we want to find the slope of this curve, because there it is. It represents the rate at 2 minutes, because it is a tangent at 2 minutes. So we want the slope of that tangent. That's just simple coordinate geometry, y2 minus y1 over x2 minus x1. Then you could call this x1 y1 and x2 y2, and you do a bit of that maths at juniors there as well. Just find the slope, 35 minus 60 over 1 minus 3.5. That obviously comes to minus 25. Subtracting the two of those comes to minus 2.5. Minus and minus positive, and 2.5 into 25 is 10 centimeters cubed per minute, and that brings us to the end of that one. And what changes would you expect in the graph of 25 cm cubed of 0.5 molar sulfuric acid we're using in the experiment at the same quantity? So let us look at that first one, 25 cm cubed of a 0.5 molar solution. Now the initial quantity used was 0.1 molar sulfuric acid, so 0.5 obviously is an increase in the concentration, so you'd expect an increase in the rate. The initial part of the graph will be much steeper because of an increase in collisions, because of an increase in concentration of the sulfuric acid, which in this reaction actually will be known as the limiting reactant, because it says that granulated zinc is in excess. So there's one of them limiting here, and that's the sulfuric acid. And then the other question there, if the same quantity of 0.1 sulfuric acid had been used but the temperature was higher, you would expect a steeper curve as well, because an increase in temperature leads to an increase in the number of collisions and the number of collisions that have sufficient energy for the reaction to occur. So that's activation energy. So an increase in temperature would cause the curve to be much steeper, and indeed in both cases the reaction will go to completion quicker. The time achieved to use up all of the sulfuric acid will be quicker if you rose the temperature, because there'll be more collisions initially and the rate of the reaction will be faster initially. And that brings us to the end of that question.